In the previous lecture, we discussed about intensity interferometer. In this lecture, we will take this concept of intensity interferometer and introduce you to something called as Hanbury-Brown-Twiss experiments in the context of classical intensity fluctuations. The important and the central point of the discussion here is to introduce you to the second order correlation function, which is generally represented as this G2 as a function of tau. And this concept becomes fundamental for one to perform Hanbury-Brown-Twiss experiments with photons, and combining the concepts of the G2 and the Hanbury-Brown-Twiss experiments leads to an important concept, including the so-called quantumness of the photon itself. And how do you determine quantumness of the photon is one of the central themes of this particular discussion. One would also be able to discuss some concepts related to something called as photon bunching and anti-bunching. These bunching and anti-bunching essentially tells you how the streams of photons are emanating from a light source, and how can you distinguish between them. And anti-bunching process is what really relates to single photon picture in quantum optics and is central to understanding the quantum nature of light itself. And finally, some basic experimental demonstrations and some pioneering experiments of photon anti-bunching will be briefly discussed in this lecture. So let's get started with the comparison between the famous Michelson stellar interferometer and the intensity-based stellar interferometer. In the Michelson stellar interferometer, what you generally observe is that you would be able to utilize two mirrors, and then you would be able to now look at the interference between the light coming from these two mirrors, and this light can be coming from stars, which means that you would be able to look at the star light which is impinged onto this particular interferometer, and then the interference pattern can help you to get roughly the diameter of the star from which you are able to collect the light. One of the difficulties of this interferometry technique is the sensitivity of this mirrors, and also the very sensitive aspect of the phase in the interferometric technique itself. And therefore, interference patterns are extremely sensitive to any alignment errors in such kind of interferometric methods. Contrast to that, the Hanbury-Brown-Twiss stellar interferometer essentially collects the intensity through this antennae, and the important aspect of such interferometer, as discussed in the previous lecture, is that the distance can be very large, which means this distance is usually called as the baseline, which means that you would be able to have the detectors at a very long distance and also collect the intensity directly into an electronic instrument, which can further process the intensity correlation as the output of this particular system. Now, why are we discussing this in the context of quantum optics is the question, and that would be evident furthermore by understanding how we are able to detect the light in such kind of interferometric measurements. Once you have a laboratory light source, in this case, let's say a mercury lamp, which is filtered for a kind of a monochromatic emission. So you essentially have a single line or close to a single line. This light falls onto this beam splitter. Part of the light gets directed to the photomultiplier tube, and other part is transmitted into the photomultiplier number 2. Here you have the intensity I1 and I2, and these two intensities can now be coupled into an integrator. The important aspect here to note is this delay generator. What it does is it adds a very controlled delay, tau, and this is the tau what we have been discussing all along during the previous discussion. that you now have this intensity fluctuation in the second channel, and as a function of the delay in this line, and the light which is coming into this particular system essentially is taking the fluctuations of the intensity in this channel as a function of time. Now, once you couple them together, you would be able to now get an average of the intensity correlation in terms of the fluctuations. Note that the time goes from t to t plus tau, and therefore what you essentially get is the time average of this fluctuation. By studying this particular fluctuation, one would be able to extract some meaningful information. And what is that information? And one of the key information what you get is this so-called second order correlation function. In the second order correlation function, what one gets is this G2, and this particular G2 comes from the fact that you now have the electric fields conjugates and also the conventional electric fields in the numerator, and in the denominator you have the average over specific times and the delays. Accordingly, you get the intensity and the shifted intensity, the whole of its average, and individual intensities, their respective averages. So this is the measure of the G2 function, and which is very crucial in quantum optics because this is related to how you can detect single photons and other kind of parameters. For example, if you take time delays, which is much larger than the coherence time, and if you take this average over this particular time scale, you end up getting for a coherent source, the this particular average essentially is equal to the average of the square of the intensity itself. This is one of the results for the conventional coherent sources, whereas for other kind of sources, this averaging process might actually differ. But this is a standard result for a coherent source, kind of a classical source, so to speak. What is interesting here is to ask what are the values these G2 can take. For a coherent source, the G2 as a function of tau is essentially equal to 1. Whereas if you take G2 for any other source, let's say for chaotic sources or some other kind, as tau reaches the value of 0, then you essentially have a value which is much greater than 1. Now, the interesting aspect is that for a quantum light source, this G2 value always happens to be less than 1. We'll come back to this particular concept in a few minutes. Before that, let's look at how does the G2 value looks like for conventional light sources, such as a chaotic light source. Chaotic in this case can be any light source which has Gaussian, Lorentzian, or any form of the distribution of intensity. So here is the chaotic source. In the case of the chaotic source, as you can see, if you take this ratio of tau to tau c, and as the value goes close to 1, the chaotic source deviates from the value of 1, and the G2 goes up as you go closer to the value of 0, which means that the tau is going closer to 0. Whereas for coherent source, this value of G2 essentially is equal to 1. So it remains a constant all throughout, and this is a characteristic of a coherent light source, whereas a chaotic light source shows this behavior. One of the important lessons in quantum optics is that you learn that if a source happens to have some kind of quantum mechanical nature, then the value of G tau as it comes closer to 1 goes less than 1, and it goes down instead of going up. That's one of the characteristic features of a quantum light source, so to speak, and you'll see that in a few minutes. But before that, let's look at the comparison for the properties of the second order correlation function for classical light. All the classical light essentially shows this property. The G2 value at tau is equal to 0 is greater than or equal to 1, and the G2 value of 0 is generally greater than G2 value of tau, as you could see in this particular situation. Whereas for perfectly coherent light, the G2 value at tau is equal to 1, and this applies for all tau. And as we saw, it applies for all the tau or whatever you have. Now, you can take various different kinds of chaotic sources like Gaussian source or Lorentzian source, and just the form of the G2 changes. Here, I need to mention that it is essentially greater than 1. As you can see, it is 1 plus. So, it will add to this value of 1 through these exponential factors from the kind of sources what you are considering. How do you go about now measuring this kind of G2 value for, let's say, a single photon source or a source which actually is emitting photons as a stream of energy packets? And essentially, you use this Hanbury-Brown-Twiss experiment, what we have been discussing. Here again, instead of taking them as classical intensity waves, you take them as streams of photons, which are actually coming into this particular beam splitter. And please have a look at this 50-50 beam splitter. Because of the fact that these particles are individual in nature, as it goes through the beam splitter, it can either reach D1 or D2, which are the detectors. Then you look at the so-called coincidence, where you essentially have a stop and start counter or a timer electronics, which gives you the number of events in the D2 and D1 channel. Once you register a click on D1, if the emission is indeed single photon, you would register the click only in one of the detectors, either in the D1 detector or in the D2 detector. The important aspect of this experiment is that you do not know which path the photon takes. It can either go to D1 or it can go to D2, and therefore you would always have some particular registry of the click either in the D1 or in the D2. If it is a single photon, it cannot have clicks simultaneously, and that's one of the important results in this particular picture. Now, the interesting aspect is that you would now ask in what ways the photons can arrive in such kind of systems. One way is to look at this so-called anti-bunch photons. You now have a stream of photons which are coming with a very well-defined spatiotemporal kind of periodicity. Whereas if you take random source like a coherent source, there is still individual photons which might be arriving as a function of time, but their gaps can be random in nature. Whereas for so-called bunched light, there can be bunches of photons which are all bunched together in an instant of time. Remember, there can be two dots also overlapping with each other, and therefore it's usually called as the bunched light. And this is the conventional light source, what we look at it. And this is where the categorization becomes very important. The chaotic source, which is a conventional light source, has bunched photons, and therefore its G2 value at 0 will always be greater than 1. For the coherent source, in spite of the fact that it's random, its value is equal to 1, whereas there is no classical description for a bunch photon, for an anti-bunch photon, and therefore there is no classical equivalence, and its G2 value will always be less than 1. What kind of systems can actually emit anti-bunch photons? One of the prototypical system is kind of a two-state atom, where you have transition from lower energy to from higher energy. There is a relaxation, and there can be emission of photon in this particular regime. This is a simplistic model, but it does work to at least understand in which way you would be able to get this stream of photons coming out. And there's a lot more details associated with preparation of states which can give rise to anti-bunched photons. So this is a crucial distinction and essentially the quantumness of the light. The quantum nature of light essentially comes from this particular viewpoint and is one of the most important categorization in quantum optics, along with some of the aspects which we have discussed in my course related to the Poisson distribution and sub-Poisson distribution and super-Poisson distribution. This acts as another important classification of light in terms of non-classical and classical way of looking at the light and its photon picture. How do photon bunches look like? If one considers intensity as a function of time, The average intensity can now be associated with this dotted line, whereas the stream of light has this fluctuation in the intensity. The photon bunches essentially come from this group of photons which are bunched together and also are above the average intensity what we generally obtain. Please remember this bunch of photons are very important because they give rise to the collective average properties such as polarization of the light beam and its phase and other kind of properties essentially arise from this kind of a picture. Here is the crux of the argument for a photon picture where the G2 value at 0 tends to be of the value less than 1. So this is an example for two different single photon sources or anti-bunch source. As the tau value goes closer to 0, you'll see that the value of G2 drops to the value which is less than 1. And this dropping below 1 is a very crucial aspect of looking at the photon anti-bunched process. So this is a theoretical framework, and it is important for one to understand how people went about experimentally verifying this. One of the remarkable experiments which was performed dates back to 1977 by Kimball, Degnias, and Mandel, which showed that if you take, let's say, streams of sodium beam and sodium atoms in this particular case, which are spatio-temporally isolated from each other, a remarkable feat by itself, and now you shine laser onto such kind of an atom, that individual atom uh, coincidentally now can emit light and that emitted light can be single photon in nature, and that is captured through this microscope objective lens, and one creates this slit in order to ensure that the light is emerging from this particular region, and then takes the light into this beam splitter. Part of it goes to PMT1, which is the photomultiplier tube 1, in the photomultiplier tube 2, and then you perform the timing measurements as we explained in the Hanbury-Brown Twiss experiment. And here is a remarkable result, what the authors observed, that the G2 value of tau is now lesser than 1. This is one of the characteristic of quantum source of light, and this is where the quantumness comes into picture. And this is essentially the quantum optical phenomena, which is of high relevance and in contrast to classical nature of light, where the G2 value now dips below the value of 1, and as you go closer and closer to the value of 0 in the tau, you see that this value goes below 1. It's indeed a remarkable experiment because one is looking at the transition in the sodium atom, and that emission is now captured through this optical source and has very interesting characteristics to understand the phenomena itself. Furthermore, one can extrapolate such kind of experiments to solid state systems. For example, one can look at quantum dots which are embedded in semiconductors. Gallium arsenide is a semiconductor, direct band gap, and you have now quantum dots embedded in them. You shine laser onto such kind of system and you project it into the Hanbury-Brown Twiss kind of experiments. And now you look at this coincidence measurements where you ask how does the G2 value look like as a function of time delay, and you suddenly see this beautiful dip. And this dip in the literature of quantum optics is also called as Hongu-Mandel dip, because Hongu-Mandel, again dating back to the epoch time, did exhibit and show in 70s and 80s that this is one of the characteristics of a single photon source, especially if this dip happens to be very kind of steep, then you have a quality of the photon source is much better. So this is usually also called as coincidence measurement. The other point I have to mention here is that it's not only the semiconducting structures. Nowadays people are interested in looking at 2D materials, and such kind of 2D materials can also have isolated kind of defects, and these defects in the 2D materials can act like single photon sources. This is a contemporary research problem, very fascinating. Such kind of systems can also be found in diamond. For example, nano diamonds can also have defects, and the defects in the nano diamonds can also act like single photon source. And these kind of materials are robust, whereas in this particular case, the experiment was performed at low temperature. The goal is to also reach the room temperature single photon source, which is one of the important kind of requirements for quantum information processing at room temperatures and related effects. So these are some very fascinating aspects of quantum optics. This also gives a very direct connection between the so-called correlation function and the quantumness of light. And I would urge you to have a look at the literature a little more closely to understand the concepts. So what we have covered in this discussion is essentially the intensity interferometer and the kind of contrast with the classical intensity fluctuation, and the important concept of the second order correlation function in terms of the G2, how Hanbury-Brown-Twiss experiments are adapted for photons, basic concept of photon bunching and anti-bunching, and finally the demonstration of photon anti-bunching through the HBT experiments using various different sources. All the discussion what I have had in this lecture is mainly from this wonderful book on quantum optics, an introduction by Mark Fox, and also there are good references within this particular book. Have a look at them. You would be able to learn a lot on the concepts of quantum optics, and also Mark Fox is somebody who doesn't hesitate to discuss about experimental aspects of quantum optics, which is an important and equally relevant question in the age of quantum technologies, and you would be able to really learn more from this particular book, including many other sources which I have been using in my course. So this gives you an overview of the quantumness of quantum optics, so to speak. I am expecting you to learn a lot more by exploring original papers and sources. I have been writing blogs on this. In the description, you will also find the link to the course blogs, what I have been writing, where I have also updated various sources, timelines, and also linked to the lectures, what I have given related to these topics. Do have a look at it. It is important for you to go to original sources, good rigorous books, and learn the techniques. Videos and also discussions are good, but they would capture only a small essence of a very deep subject. And importantly, quantum optics is not only just about looking at things in an abstract way. They have very interesting applications which are emerging in the context of quantum technologies. So I would urge you to have a look at them in greater detail. And I'm hopeful that you would be able to learn a lot more than the lectures what I have been giving on this platform. So until next time, bye bye.